Hi, and welcome to the fourth module of our programming course. In this module 4, we're going to talk about binary numbers. And in this video, we'll be going through why do computers use binary numbers. We will see how they actually work. And then we are going to use them in a C program. So let's get into it. Why don't we use base 10 numbers, so the normal numbers you use in everyday life, in computers? We all intuitively know how decimal base 10 numbers work, so why wouldn't we just use them? There are several advantages to using binary. The easiest to understand is signal integrity. So you can imagine if you have 10 different levels where the signal could be, then even a little bit of interruption could affect this value. And now you're just guessing, is this number going to be the one where it actually sits, one higher or one lower, or even worse? In comparison, in binary, the difference is a lot easier, because we can easily say if a given voltage is, for example, ground level or not. We can put anything above a certain voltage to be 1, and anything below it to be 0. And we don't have to do any guessing. In addition, the hardware becomes simpler as we can use transistors, that is, small pieces of semiconductor that can be controlled to either let a current flow through it or not. And if a current flows, we can call the signal to be a 1 and otherwise a 0. Using binary also allows us to implement error checking techniques like parity bits and checksums to detect and fix any errors that might have happened. So, in conclusion, using base 2, so binary numbers, lets us make smaller, faster, more energy efficient, and more reliable computers than using any other base. So, let's then understand how binary numbers actually work. And to kick things off, it's important to first understand how our normal number system works. In base 10, we have 10 symbols, from 0 to 9. But, oh no, we have run out of numbers. What do we do after 9? Well, we start over. We take a new digit, so now we have 2 buckets where we can fill symbols, and naturally from that point onward, we continue with the same steps, until at some point we hit the same problem with 99. Shoot, what do we do now? Well, we just do the same trick again. Take a third bucket, so a third digit, and start over. Go 1, 0, 0. If only binary was this easy. And foreshadowing, it's exactly the same. First we have 0 and we have 1, and we run out of symbols. So we take a new digit and we do the same thing. We go 1, 0 until we hit the wall again. Now we're at 1, 1. So we take a third digit. We go 1, 0, 0, and now we got up to 4. Once we continue, 1, 0, 0, 0, and now we're up to 8 different states. And you may notice a pattern here. We go from 2 states to 4 to 8 to 16. This is not a coincidence. In base 10, we have to take a new digit once all the odd digits have turned to 9, which is our highest order of symbol. In base 2, 1 is our highest order of symbol. So we go 1, 1, 1, 1, 1, 1, etc. So the question is, how does the number of digits relate to the number of states we can represent? In base 10, when we have 1 digit, we can do 10 different states. When we have 2 digits, we can do 100, and then 1,000, and then 10,000. In base 2, we can do 2 states, then 4, then 8, and then 16. So in base 10, we can do 10 to the power of number of digits. And in base 2, we can do 2 to the power of number of digits. So let's then see how these binary numbers relate to common data types. When we have a variable that is of type character, it means that it has 8 bits inside it. With 8 bits, we can do 256 different states. So this means that a variable of type char can do -128 to 127. And if it's unassigned, so it can't be negative, then we can go from 0 to 255. With 32 bits, we can do over 4 billion different states. And the same thing here. If we have a sign, we can do half the number of values, but we can do in both directions. Okay, so now we understand that binary numbers aren't that different from our normal base 10 numbers. So let's take a look at some code. Here I have a very basic function I made where we first create an unsigned char variable and set its value to 240. As we saw, this unsigned char can do any integer between 0 and 255. So 240 is just fine. I've also made this function that prints 8 bits. And if we run this program, we see that it prints 1111 0000. Now, how can we be sure that this actually works? Did I print the correct thing? And I don't want you to trust my code, because I don't trust it myself. And the most important thing about computer science is that always test your code. Never trust it straight away. And one way to test this code is to calculate the output we got from this printing function. So let's take a closer look. Now, before we can actually calculate what the binary value is, we should first understand how do we calculate numbers in our normal base 10. I can say that this is 240, but what does it actually mean? How do we know what 240 is? The rightmost digit is responsible for telling us how many ones there are. The second number from the right is telling us how many tens there are. And the third for how many hundreds. And obviously we know this by heart, but it's gonna help us understand binary numbers. Once we sum this all together, so 2 100s, 4 tens and 0 ones, we get our value, 240. And now base 2 is just as easy. Here, the rightmost digit is responsible for ones, the second for twos, then fours, then eights, 16s, 32s, 64s, 128s, and onwards. So now we can do the same thing we did last time. We have 128, we have 164, we have 132, 116, and the rest are all zeros. Once we sum this all up, we can see that it all sums up to 240. So now we can be quite confident that our printing function works. Now, remembering how binary numbers and base 10 numbers correlate with each other is not easy. I wouldn't remember how 240 is equal to 11110000. And for that reason, we have come up with hexadecimal numbers. So they go from 0 to 9, and then they go A, B, C, D, E, F. So we have 16 different symbols, and with these we can easily write binary numbers. So let's take a look. If you would want to write a number we got with 240 with hexadecimal, we start with 0x, which tells the computer that this is going to be hexadecimal. Because 4 bits, so 4 binary digits, can express 16 different states, it means that when we want the first 4 bits to be 1111, we should pick the highest symbol available, which is F. We also want the lowest 4 bits to be zeros, so we should pick 0 there. That way our number becomes 0xF0. Now, we can test that we got the number right by printing our variable 2 as well. And we can see that it got the same answer as 240. Okay, so now that we understand binary numbers, and we understand how to use hexadecimal numbers, let's take a look at my printing function. At the first line, I define a variable called bit_iterator. It takes the value of 0x80, which means it's hexadecimal, and the first 4 bits correspond to hexadecimal number 8, and the last 4 bits to 0. And in my commented line, you can see how it translates to decimal and binary. In my first variable, there is only one bit as 1, and that is the leftmost bit, because we want to print that first. Then we have a for loop that loops 8 times, once for each bit. We make a variable called current bit value, and we initialize it to 0. We set its value to 1 only if the input is 1 at the same position as the bit iterator. We then print the current bit value, and then we do a shift operator on the bit iterator variable. What this does is it moves all the bits in the bit iterator variable one step to the right. That way we can get all the bits out of the input character. And in the last line, we print the line change. So that's a short intro into binary numbers, and I hope this helped you out a bit. And yeah, see you next time.